Welcome back. In this session, we're going to go through the different dimensions that are involved in the experimentation design. We are not going to go deep into any of them. We're just going to list them so that you can get a feel for the complexity that's involved. So we have 5 running examples that we're going to use throughout the sessions. The baseline is E1, that's a deterministic function. It's our host health anomaly scoring. Then we have a couple of classifiers. The first one is a machine learning train classifier, and the second is the same classifier, but in a GenAI few shot version. And then we have a couple of typical GenAI use cases. One is self-solve of customer support request, and the last one is a text summarization problem. So just as a refresher, as a reminder of the previous session, this is the health anomaly scoring function. There is no AI, simple function, 2 parameters in, does a check on parameter, and then returns a formula based on the input parameters. Now the ML classifier is where things start to be, let's say, interesting. We have a training phase where we want to build a model that can predict and classify tickets into one of 5 different categories. So we have this training step that produces a classifier, and then we have a runtime, prediction time, inference time thread where we use our train classifier to actually try to predict tickets classifications. The same version can be done using GenAI, so no training. We take a pre-trained general purpose model, and we do classification using a few short examples. So we provide definition and examples for what these 5 classes are, and then we hope that the LLM can understand what we want to say in terms of these classes and is able to classify tickets for us. Let's now go to a more difficult example, that of self-solve via clustering. So what we do here is we assume we have a bunch of tickets, say 100,000 or so. We first run a clustering algorithm, and we cluster these tickets into groups. And typically we want to group together tickets that have the same resolution. And then we process tickets in a cluster with GenAI to extract what is the recommended or working solution for those kind of tickets. So at the end of this, let's call it training process, we have a clustering method with clusters, and we also have solutions recommended for each cluster. So at runtime, when a new ticket comes in, we can first match it to one of the cluster, and if we are successful in matching, if we find the match, then we can just read the solution that we have computed or derived for that cluster. The final example is a classic text summarization example where we have a message, in this case a customer request message, and we want to summarize the content of the ticket. Now let's think about what we need to consider when we design experiments for such system. The first one seems obvious, is where I find people struggle the most, is the ability to define what is the system that is under test. So what are we doing the eval of, and what is an example of one data point. Then the second dimension is the ability to define the questions we want our experiments to answer. What are the assumptions under which we run the experiments, and what's the baseline that we compare against. Then we have the issue about selecting the right data sets that stress the aspect of the system we want to stress. We define the evaluation workflow and how we assess quality of the outcomes. specifically how we access the ground truth. We then define the experimental conditions, the conditions that we want to test for our system. And finally, we need to think about reporting. So how do we report the results? How do we discuss limitations? What are the experiments that we have done, like mirror reality, the condition of the system under test that we had are actually representative of what we are likely to find in production. Now let's go into each of these dimensions one by one. Before we go through one by one, let me just take one example and walk through all these dimensions. So if we take for a moment as the example our machine learning trained ticket classifier, then in one possible, let's say, design, the system under test is our machine learning classifier. So it's our ticket classifier, and one data point, one sample is for us, one ticket that we want to classify. The goal we hope to achieve with the system is to have an accuracy of at least 90%, and we want to be at least 10 points better than the baseline. The baseline for us are a simple keyword-based classifier, and maybe also a logistic regression classifier. As dataset, we use a public dataset called ByText. We use stratified held out test set of 500 tickets. So it's balanced across the 5 classes. We keep a validation set for hyperparameter selection. We know that data can vary in length, language, domain, but in our experiment design, we just use the data in this ByText dataset. In terms of the evaluation workflow, we train model, we select hyperparameter on the validation set, and then at the end we run the numbers on the test set. We focus on the accuracy, which is our main target metric. We also measure F1 and a per class confusion matrix to understand better where and when our system failed. We need the ground truth. In this case, we can either take the ground truth that is present in the dataset, or we can say we take, for example, the human labelers and we ask them to label the tickets, or we use AI to do that. But clearly, if we use AI, then this can be circular. So for now, let's assume we use human. We'll get back to this, to the AI as labeler and as judges later. For now, let's assume we have 2 humans and we only use as test set or train set the items where the 2 humans actually agree on the class. Our baseline is rule-based and logistic regression, and our experiment space is deep neural network of different depth and sizes. And when we report, we commit to report our main metric, which is accuracy, plus credibility interval for the accuracy, per class F1, and taxonomy of the error, and we're going to report on the limits. For example, English-only datasets and only one dataset. Let's now see some example of system under eval. For example, for our LLM-based classifier, so the one that is pre-trained, our system is composed of mainly 3 parts. There is the model, the large language model that we use to classify. There are the examples that we give, our few short examples, and then there is the prompt that we carve around the example. So when we are thinking about doing evaluation, we need to understand which of these three aspects we are focusing the eval on. Maybe we are just looking at the end-to-end, so we consider all these three aspects separately, or maybe we want to focus on one of these parts and see how the system performance change as we change one of these three parts. For self-solve via clustering, things are even a little bit more complex. We have a bunch of moving parts here. We have first the clustering algorithm that itself has many different options and many different decisions we can take. Then we have the solution extractor, this process of going through tickets in a cluster and trying to carve out a common solution. And then at runtime, we have the cluster matching. So the question there is, are we able to correctly match tickets to clusters, or maybe even correctly say that there is no matching a cluster for a ticket? So lots of moving parts. When we are doing eval, we need to be clear about what is it that we are doing the eval of. Also, something I think very important here is the notion of what is a data point. We can consider a ticket as a data point at runtime, right? But because we have a clustering step, and because we need to judge also how good the cluster are and how good the solution for each cluster is, then we also could say that a cluster is a data point. So we don't just want a large number of tickets, we also want a large number of clusters because we are making assessments also per cluster in terms of, for example, how good the solution for a cluster is. Let's take a look now at our second dimension, the goals and metrics. And for example, for the machine learning classifier, our example number 2, we can think that the question is that we want to answer is how accurate can our ticket routing be? And as a baseline, we can take a logistic regression, for example. The assumption is that maybe we only consider English language tickets and relatively short, and our key metrics is primarily the accuracy, and then we also consider F1 on a test set as a manner to investigate the quality or lack of quality of our methods. Similarly, for the GenAI version of the ML classifier, maybe the question we want to answer is, can we get the same performances that we get with the trained model, but without having to manage a specific machine learning model? Because that will make our life simpler, maybe. And the assumption that we have may be the same as the previous case. Maybe we assume that our few shot prompt has 4 examples per class, and we know that we have only 5 classes, so it's fairly small. And maybe key metrics again here, the accuracy, and maybe here we also care a lot about cost and latency per ticket, because this can be a bit tricky when we use GenAI, and they can cause high cost, higher possibly than a traditional machine learning model. For our self-solve, the question we may want to answer is, can we manage to answer at least half a ticket? So at least for half a ticket, we get the system to kick in and propose an answer. And when the system proposes an answer, how many of them have a score of 4 or more? So we want a high coverage. We want a large number of tickets, large enough so that it makes sense for us to deploy the system. And then when the ticket is covered, it's in scope of the problem we think we can self-solve, how often is our solution correct? And the assumption is that, once again, maybe they can be on the language. We can also assume that maybe there is one clear dominant topic per ticket with not much fuzziness, right? And our key metric can be percentage of tickets that are covered and get a score of 4 or more in terms of the quality of the resolution. And then simpler case, the summarization problem. Let's say that, for example, here the key matrix is faithfulness. How faithful is the summary compared to the original text? Maybe the assumption can be that the text is reasonably small, and the question that we want to answer is, can we get a faithfulness of at least 4 for at least 90% of the summary? And that's our let's say bar that we want to beat. Let's now come to the eval workflow, and let's start from, I think, the most complex case that we have, this self-solve system. So as we discussed, there is a small training part where we develop clustering, and for each cluster we extract solution to solve cases in the cluster. And then at runtime, when we get a new case, we match it with a cluster that is more relevant for that case, and we just read what is the solution for that cluster. And as you may remember, when we discussed this, we also discussed the possibility of having some kind of judge that takes the input and the output of our magic self-solve system and then tries to say whether the solution proposed is good for the case at hand. And it spits out, I don't know, a bunch of metrics, let's say mainly a correctness metric on a 1 to 5 scale, right? And let's assume that this judge is actually, once again, AI. So we have a large language model that takes the input and the output of our system and tries to judge whether the output makes sense. So this means that the workflow we have is something like this. We have at the top a training time phase where we derive our system. We have a runtime phase where we take a point, a case, and we try to solve it. And then we have the eval, where we take inputs and outputs of the cases we have tested, and we derive measures, quality measures for our system. And so that's the core of the eval workflow. There is another part which is also important to mention, which is the judge calibration. So we don't know at the start whether the judge that we have designed is a good judge. So we go through a judge calibration phase where essentially we do two things. One is on a validation set. We try to assess the judge, understand when the judge is judging poorly, and we actually iterate on the judge. So this is different from, let's say, iterating on the model or system itself. We want to iterate on the judge because we want to have a reliable judge. And then once we have that, then we test the fact that our judge is actually reliable by picking a test data set where we run the LLM judge, but also we have humans to assess the judge output. And by doing this, we assess how good of a judge we have. And we're going to see later in this set of sessions what is the impact that judge noise or that the error in this judge can have on the quality of the eval that we have. So the main suggestion in terms of the eval workflow is, first of all, draw the eval workflow as a diagram. That helps really a lot to understand and make sure that we are taking into consideration all the aspects and we can communicate properly what is the experiment focusing on. Second, as the key point, is decide how do you derive the truth or the correctness of the answer. You can have human labels, you can have LLM as a judge, you can have label derived in some way from the data. And one point I would strongly encourage here is try to use LLM as a judge when possible. LLMs are fantastic judges when prompted properly. So for many cases, it really works well. And it's an approach that can scale. Humans do not scale. And also humans find it very hard to assess many tasks that maybe the LLM can often do better because, for example, they can consider all the information provided to them properly, while maybe for human it may be difficult to process a large amount of data, for example, to come up with a good summary or with good, let's say, insights from a task. The third aspect, which is also, I think, very important, is try to measure disagreement and subjectivity. Is it easy? Is it, let's say, objective, the outcome of a task, or is there some subjective aspect involved? So would, for example, two humans disagree? And basically what this matters is that the judge is also a system under eval. Doesn't matter how we judge, whether it's humans or whether the LLM. If it's human, we need to measure disagreement. If it's the LLM, we also need to measure disagreement between different models or different judge prompt and get a sense for how brittle the judgment is. And you typically, if you use the LLM judge, you typically want to validate with humans to see whether humans and the LLM come at the same conclusion in terms of judging, and if not, try to go to the bottom to why that is the case, and to some extent, who is right, whether the human or the LLM. So in summary, what we can say for our use cases is this. For E2 and E3, our classifiers, we just assume that we trust the ground truth that comes with the data set. So we're going to have a training, validation, and test set, and that's our workflow. We really have no ground truth, let's say, problems here. For E4, we have discussed how we can think about the evaluation workflow and the judge. And for summarization, that is also follows similarly to what we said for E4. Most likely, we're going to want to have an LLM judge that judges the quality of the summary. We're going to describe to the judge what a good summary looks like, maybe give some example, and then we're going to calibrate the judge on a given number of human-generated summaries, or we're going to calibrate based on 100 LLM-generated summaries, and then we're going to see whether the judge is consistent with the human ratings for the same summary. And once again, here we most likely are going to have a validation set where we tune the LLM judge, and then an actual test set where we test the calibration of the judge. This is separate from the notion of validation and test set for the system, so we need validation and test for both. So in terms of the data selection and sampling dimension, let's consider also the simple deterministic function here, and remember how we described that for this kind of function, we try to pick points that are kind of representative of the space. We know the space, the function is fairly simple. And the idea is that if we do well on this point, we do well on every point in the space. Now, what about the other cases? For the machine learning classifier example, so E2 and E3, I will say in both of these cases, here we assume that we just use a public data set, which is labeled. We take it at face value, which means we assume it is labeled correctly, and we have no specific reason to sample a subset. I think is the data set is like 27,000 or so customer support cases. So we can use some train validation test split to train the model, validate, pick the model that performs best, and then test it on the test dataset. And one sample here is one customer support case. The self-solve case, it's a little bit different in that, remember what we do in that case, right? In that case, we first cluster the records, so we build a clustering model, and then for each cluster, we try to derive a self-solve solution. And at runtime, at prediction time, we have a way to match new customer support requests with a cluster, and then draw the solution corresponding to that cluster. So here we may have, let's say, many customer databases, or in simple cases, one customer prod database. Let's assume we have 100,000 tickets or whatever. But what matters is not just the number of cases. What matters is the number of clusters. So we want a data set that lets us validate and assess whether our pipeline works well. And to some extent, if we have 100K tickets and they belong to the same cluster, then we really have one example where we test the whole pipeline end to end, because we have only one self-solve solution, right? So one option is to say, okay, I want to have tickets that are diverse enough to give me around 20 clusters, and to some extent you can play also with the clustering method to get clusters at a granularity and at a number that you like, that works for you. And then maybe for these 20 clusters, I create a self-solve solution, and maybe I have human labelers that take a look at this 20 cluster and decide whether I've done a good job or not. We'll see later whether 20 is a large enough number, but for now, let's assume that that's what we do. And for summarization, maybe same thing. We use the same 100,000 prod tickets. Maybe we restrict to tickets under 1,000 words or whatever. And then we take them all. We don't sample a subset. Maybe the reason why we don't sample a subset is that we don't have humans label all the 100,000 summaries. We create an LLM judge that can assess whether the summary works fine, and maybe we just have a human to then calibrate the LLM judge. And we'll talk about this in a second. But I think the core idea here is that as we increase confidence in LLM also as a labeler, as a judge of whether answers are correct, we don't need to scale down the sample as we did in the past. We can have and keep fairly large samples, and maybe actually continuously have new test tickets from new prod database, right? Because once we have the ability to validate at scale, then we are not constrained by the human labeling factor. So a few principles in terms of the experimental condition. One is give a name to each experiment arm, so to each recipe of your model, your prompt, your data. Give it a name so that you can clearly identify the experimental condition. Try to design different experiments so that you change one thing, so you can try to understand the effect that each individual change, for example, different model or different prompt, has on the final result. When you are comparing different arms, try to use the same judge. and make the comparison per item, so how the different arms perform on the same data points, for example. If you have a baseline, try to be fair. Like if you spend a lot of time tuning your, I don't know, super powerful, let's say, model, and your baseline is, I don't know, locally running open weight models, try to be fair to the baseline and maybe fine tune the baseline model as well. So you can have a reasonable comparison for how much a better model give you on top of a simpler one. Once you run experiments and you have several dimensions, so we, for example, already saw, different models, different prompts, different contexts, different templates. At some point, conditions multiply, and you get into the exponential complexity problem of trying to assess a set of different conditions. So what you want to do here is try to make sure that you are very clear what the primary comparison that you want to make are, and declare them. And maybe on the validation set, you try to come up with what are the interesting conditions that for you give you the best performances, then pick one or two, and then you touch the test set only on this one or two key, most powerful condition. So do not repeat touching the test set with multiple different conditions, because that leads to biased results, and we're going to see how biased. Also keep in mind that in GenAI, the notion of same is a little bit slippery. Sometimes you need to pin the temperature, the order of the example, the model version, and as they change, your results may also change, so try to fix them in the experiment that you run. So in this slide, you just see a few examples for possible experimental condition for our cases. For example, for the ML classifier, we may try different ways to embed the text. We may try different deep neural network models, different approach to regularize the output. We keep constant the train and test split, maybe the preprocessing, and we fix the random seed so that we make it easy for results to be repeatable. For the GenAI version, we may, for example, change how many examples we put in the prompt. We may change the model, and maybe we keep constant the prompt template, the set, and the output format. And similarly, you can have similar experimental variations for the other examples. We're going to see reporting in detail in a future session, but just in terms of general principle, when we report on the experiment, first we start from the experiment design. So all the dimensions we have seen, we need to be very clear about, how we run an experiment, what we were trying to measure, what are the goal data sets, and so on. Then in terms of the answer, some important principles are: never report a bare number, always report the uncertainty around the number. Remember, if we are reporting something and we don't know what is the uncertainty behind the number we are saying, then that number is completely 100% meaningless. So we need to be very clear about what is it that we know and what is it that we still don't know. Remember, especially if you're doing classification, to also report per class results. We find that typical decision maker find that important to derive whether you want to put a model in production or not. Make sure to be upfront about what is the insight, what you have learned from the experiment, especially if that could swing the decision on moving to production or not. Be very clear about the limits. So what are the limitations of the conclusion that you've made? What are your conclusion applicable to? For example, only ITSM, only English language ticket, only tickets that are short, and so on. And then state whether your results are reproducible or not, and hopefully they are. Like if the results are not reproducible, then I think the question would come as to why that is the case, and whether the experiments are even meaningful if we cannot reproduce them. And as you know, reproducibility is kind of the heart of science. The final point I want to mention is about an example of what many people consider bad experiment design, and definitely bad reporting on experiment. I don't know how much truth there is to the story, but as many of you know, the space shuttle Challenger broke down during re-entry, and all the astronauts lost their life in that. And some people believe that part of it is due to experimentation and reporting on the experiment. So specifically, it seems like this slide was presented in terms of experiment run after liftoff, when people observed that some foam detached from a part of the space shuttle and hit a coating on the wing. And the experiments were designed to understand whether the space shuttle could re-enter safely despite that. And the thing that people call out in this slide is this slide was supposed to report on experiment. It's one of many slides reporting on many experiments run after the shuttle launch. So it's not just one thing. So people in the meeting were listening to lots of experiments and seeing lots of slides. As you saw, this slide is very complex, lots of bullet points with different sizes. The title leads to a conclusion, which is conservatism. So like it's an optimistic conclusion. And I think the important part and the criticism of people is that the important part in these slides are this part in the blue rectangles that you see at the bottom, and they are casually mentioned there in a small font. So we are saying, hey, we have run the tests. The tests seem to be very optimistic and give us a very encouraging result. But then, oh, by the way, test results do show that it is possible a sufficient mass and velocity to penetrate the coating. And if you see the bottom line says, oh yeah, we ran an experiment, but the flight conditions are completely outside of our test parameters. So the volume of ramp is was 1920 versus 3 in our test. So it's completely different test condition. So I think the lesson here is as we report, we need to report on whether we believe and why. We believe that the experiments that we ran on the data that we ran them is actually representative of production. And we need to be able to kind of defend this statement. So that's all for this session. We have seen the different dimensions of experiment design very quickly. And now in the next sessions, we're going to go through each of these design dimension, and we're going to see what are the caveats we need to be mindful of. And also we're going to see which kind of uncertainty and how much uncertainty each of these dimensions piles on, and what we can do to manage it and to reduce it.